Geometry of dynamic tetrahelix and field structures. Part 4. The core field structure, which is a unique transformational tetrahelix, will be examined as a model for field structures, and the modified tetrahelix system will be introduced. Part 4. Core field structure and the modified tetrahelix system. The tetrahelix with subsequence 211-21212 has some unique transformational properties not seen in other tetrahelix. At a twist angle of exactly 60 degrees, this tetrahelix transformed into a structure with 4 axes of symmetry, like that of the tetrahedron. All the other tetrahelix that I have examined only have 1 axis of symmetry. I will refer to this tetrahelix as the core field structure, CFS, which could be useful in modeling field structures. I will also introduce a new tetrahelix construction method for exploring the CFS referred to as the Modified Tetrahelix System. Core field structure, CFS. The CFS has similar geometric properties like that of the Clinton field structure referred to in field structure theory by Don Bridell, except the CFS allows for overlapping elements in its structure. Could these closed-loop circuits be used to represent or model the behavior of field structures? To address this question, we'll take a deeper dive into exploring the properties of the CFS structure. Formation of the core field structure. The following video illustrates the transformation of this subsequence from a twist angle of 180 degrees to 60 degrees. At a twist angle of 180 degrees, the tetrahelix forms a linear wave structure. As the angle decreases, the tetrahelix transforms through numerous fractional harmonics that have a single axis of symmetry. At a twist angle of 60 degrees, the tetrahelix forms the CFS, which has 4 axes of symmetry. The tetrahelix forms a linear wave structure at a twist angle of 180 degrees. As the twist angle decreases, the tetrahelix loops around itself and transforms through numerous fractional harmonics that have a single axis of symmetry. Then, at a twist angle of 60 degrees, the tetrahelix forms the CFS, which has 4 axes of symmetry. The total length of this tetrahelix is 240 elements. The CFS only consists of 24 elements. So, the structure you see here has looped around itself 10 times. This demonstrates how the arcs perfectly overlap each other. CFS and the Modified Tetrahelix System. After further examination, I realized that the twist angle of 60 degrees had some very interesting properties that transform the behavior of the classical tetrahelix. I developed a new tetrahelix construction method for exploring the CFS, called a Modified Tetrahelix System. The Modified Tetrahelix uses a different set of twist angles that have been phase shift inverted by 180 degrees. As a result, this new model uses 3 different twist angles, 60 degrees, 180 degrees and -60 degrees. These new twist angles are represented in the tetrahelix subsequence with the following digits. 1 equals 60 degrees, 3 equals 180 degrees, and 5 equals -60 degrees. As a result, the CFS has a subsequence of 1515151 when constructed as a modified tetrahelix. The remainder of the presentation will focus on the unique properties of the modified tetrahelix system, and no twist angle scaling will be used in this section. Twist angle phase shift inversion for modified tetrahelix. These diagrams illustrate the phase shift inversion of 180 degrees used for a modified tetrahelix. The diagram in blue shows the twist angles used in a classical tetrahelix. The diagram in red shows the twist angles used in a modified tetrahelix, which is the result of the 180 degrees phase shift. Modified Tetrahelix System. From the classical tetrahelix perspective, the face connections of the modified tetrahelix are not flush, but phase shifted by 180 degrees, but the face centers are still aligned with each other. Here we have the minus 60 degrees twist, the 180 degrees twist, and the 60 degrees twist. Modified tetrahelix arc element. The use of arcs as elements of the modified tetrahelix allows us to look more closely at the internal structure of the CFS. This reveals the interaction and overlapping of elements in the tetrahelix more clearly. Here we have the minus 60 degrees twist, the 180 degrees twist, and the 60 degrees twist. Internal structure of the CFS. Now we will take a closer look at the internal structure of the CFS. At first glance, the CFS only appears to contain 18 arcs. 3 at each of the 4 vertices, 12 arcs. 1 at each of the 6 edges, 6 arcs. When in fact, the CFS is constructed with 24 arcs. So, there are overlapping arcs in this structure, which is an integral property of the CFS, which will be explored further. In the next video, the twist angle is slowly scaled to reveal the overlapping arcs. CFS overlapping arcs. The overlapping arcs in the CFS are revealed as the twist angle is slowly increased, and this exposes its 24 arcs. CFS overlapping arc locations. In order to examine the overlap within the CFS, the arc elements will be replaced with a geometric-compatible truncated octahedron, a space-filling shape. What this reveals is that there are only 10 unique element locations for the 24 arcs of the CFS. This array of 10 truncated octahedrons forms a half-populated space-filling matrix. Each vertex of the CFS represents just one element location but with 3 different orientations. Each edge of the CFS represents just one element location but with 2 different orientations. This matrix of arc locations can be extended in all directions, which represent an array that constrains the arcs of the modified tetrahelix to reside on this space-filling matrix. Multi-loop CFS configurations. The CFS was discovered in the simulator, constructed as a single-loop modified tetrahelix. But after closer inspection, you will see that there are also smaller modified tetrahelix that can be arranged and bonded together to create the CFS. There are 4 possible multi-loop configurations for the CFS. There is a 1-loop solution for the CFS, as well as a 2-loop solution, a 3-loop solution, and a 4-loop solution. Physical models will be used to construct these multi-loop CFS using smaller modified tetrahelix. 1-loop solution for the CFS. Loop consists of 24 arcs. Each of the 6 edges is a pair of arcs. The full sequence is 15151551, repeated 3 times. Construction of a single-loop CFS. This video illustrates a physical model of a single-loop, 24-arc, CFS. As the CFS was constructed, the overlap at the edges gets resolved physically, resulting in the arcs being weaved or adjacent. Weaving is not a requirement to hold the structure together, since the arcs of the tetrahelix are bent and twisted into this shape and its own torsion holds the structure in place. The direction of flow at the overlapping edges can be either in the same or different directions. 2-loop solution for the CFS. The subcomponent loop consists of 12 arcs. The middle/common edge consists of 2 overlapping arcs. This is the full sequence for this subcomponent. Construction of the 2-loop CFS. The subcomponent is a 12-arc loop, with this subsequence. The CFS can be created from 2 of these subcomponents. When the 2 subcomponents are brought together, the arcs have a natural alignment with each other. In this example, the subcomponents are bonded with parallel adjacent arcs that require no weaving. They could have been weaved, but that requires a cut and rejoin step and explanation. 3-loop solution for the CFS. The subcomponent consists of 8 arcs. The full sequence is 1, 1, 5, 5, repeated 2 times. Construction of the 3-loop CFS. The subcomponent is an 8-arc loop, with this subsequence. The CFS can be created from 3 of these subcomponents. When the 3 subcomponents are brought together, the arcs have a natural alignment with each other. In this example, the subcomponents are bonded with parallel adjacent arcs that require no weaving. They could have been weaved, but that requires a cut and rejoin step and explanation. 4-loop solution for the CFS. The subcomponent consists of 6 arcs. The full sequence is 1, 5, repeated 3 times. Construction of the 4-loop CFS. The subcomponent is a 6-arc loop, with the subsequence 1, 5, repeated 3 times. The CFS can be created from 4 of these subcomponents. When the 4 subcomponents are brought together, the arcs have a natural alignment with each other. In this example, the subcomponents are bonded with parallel adjacent arcs that require no weaving. They could have been weaved, but that requires a cut and rejoin step and explanation. Part 4 Wrap-up. This concludes Part 4 of the presentation on the core field structure, CFS, and the Modified Tetrahelix System. In Part 5 of the presentation, the matrix of the Modified Tetrahelix System will be described.